In this video, we're going to talk about linear regression and how we can use points to find an equation that will fit those points, what that equation means, and how we can use it. So linear regression is also known as the least squares regression line, or LSRL. That's how you'll often see it written, as LSRL. And the big idea here really can kind of relate to this picture I showed. We want to minimize these differences between the line and the data points. And that makes sense. You want to place the line such that most of the data points are close. Okay, so this minimizing idea, this is a calculus idea. And the reason we square these differences is so we don't really care about them being above or below the line. And we don't really ever use absolute value. So that's why these squares are drawn in, because you can see this is a difference and then squared. And really it comes down to adding up all the areas of these squares, right? And we want to minimize the total area. So it actually, because we're dealing with y values, right, the difference in y values, and the y values along here are reliant on x values, it's actually a multivariable calculus optimization step, which you don't really need to know, but it isn't a difficult proof. But really, for the purpose of AP statistics, we mainly use technology to do this. But the whole point is to minimize the sum of those areas. And again, the reason they're squared is to make sure that we don't have any negative values. So for the most part, we're going to use our calculator to do it. Let me explain here some notation. You see here, it's a y with this little thing. This is called y hat. And what that means is that it is a regression equation, meaning we are giving an equation where not every point lies on the line. Rather, it is the best fit for the data. Okay, so let's quickly, this is my aunts and uncles' data from my class. Let me quickly calculate the regression equation using the calculator. All right, so I have already put the data into it, so you can have the data in your lists. And then you go to Stat, Calc. We're going to go down to number 8, linreg a plus bx. This is the same one we use to calculate the correlation. Okay, my explanatory is in list 1. My response is in list 2. I'm going to leave the frequency. Store regression equation. This represents the fact that you could tell it, I want this equation to be put in Y1. We could go to like vars and say, I want this to be put in Y1 when I'm done, so I can use that equation later. And let's calculate. And there it is. Okay, negative 1.29 is the y-intercept, and 1.34 is my slope. And you see the correlation on the bottom is 0.679. So here's how we will write that. And we like to put our equation kind of in terms of context. So I'm going to write that our cousins served as our y value, right? That was our response. So we're going to write cousins hat equals our y-intercept was negative 1.29 plus 1.34 multiplied by the number of aunts and uncles. I'm going to just simplify there a little bit. You'd normally write it out, but I'm just running out of room. So this is our equation that we'll use to be able to predict how many cousins someone has if we know how many aunts and uncles they have. Now, I wanted to just call you, in this course, there are really about 5 definitions that you just need to know, and you need to be able to basically fill in the blank with your context. And the first 2 in AP statistics we're encountering right now. And they are the slope and y-intercept. And the slope is the amount by which the response is predicted to change when the explanatory increases by 1 unit. And really, I think a lot of people have no problem with this definition, but I would just urge you to really get in the habit of using the word predicted. Because every time someone has 1 more aunt and uncle, they're not going to automatically have 1.34 more cousins. That's the predicted increase. So we would say the amount by which the number of cousins is predicted to change when the number of aunts and uncles increases by 1 unit. That's the meaning of our slope, okay? So I guess, yes, 1.34. Now the y-intercept, this again, the word predicted is so important. The predicted amount of the y variable when the x variable is 0. So negative 1.29 is the predicted number of cousins when the number of aunts and uncles is 0. Of course, this is an impossible number, and sometimes that happens with the y-intercept, that you have a number that's not possible. We're not going to have negative 1.29 cousins, but that's still our interpretation of it, okay? So I would really get in the habit of using those definitions, and again, be very careful to include that word predicted, right? The amount by which the y value is predicted to change, and the predicted amount of y variable. All right, let's use this equation. All right, so I've once again written down my least squares regression line. Again, don't be thrown by the acronym here, LSRL, least squares regression line. Number of cousins, or cousins hat, is equal to negative 1.29 plus 1.34 times the number of aunts and uncles. So to predict the number of cousins for a student with 6, of course, we would just plug this in. We would say it's negative 1.29 plus 1.34 multiplied by 6, and you could certainly type that into your calculator. This is what's known as interpolation. And what interpolation means is, can we predict with confidence an outcome within the domain of the data we have? And our domain here is, we've got all the way from 3 aunts and uncles up to, I guess, 13 is our highest. So 6 is inside that, right? That's inside the data we have. So that's why it's interpolation, inside. So predict the number of cousins for a student with 9. Again, this is really the same type of thing, negative 1.29 plus 1.34 times 9. And again, this is interpolation, okay? Now, predict the number of cousins for a student with 32 aunts and uncles. So we'd say, well, negative 1.29 plus 1.34 times 32. Well, 32, we don't have any data that reaches that high up. This is what's called extrapolation, okay? Because it's outside that range. Now, really quickly, we don't really ask you anymore to do any of this work by hand. You basically find all of the parts using your calculator for linear regression. But I just wanted to point out that the slope, 1.34, the equation for this is actually fairly simple, and I think it's just worth visiting about for a second. The equation for slope is correlation multiplied by sample deviation of y and sample deviation of x. Okay, the correlation part of this, right here, this tells us direction. Right? If correlation is positive, that means we have a positive association. If correlation is negative, we have a negative association. So that part of it gives us the direction of our line. Okay? And then it's change in y over change in x with the deviations. This is how y is varying. This is how x is varying. Okay? So it's a pretty easy formula, and that's and beyond that, to calculate the y-intercept, we use the sample means. We ensure that the sample means are on the line. And I bring that up because kind of the simple algebra step here, once you answer a bunch of questions like this, would be, well, okay, what if I told you how many cousins someone had? Could you tell me how many aunts and uncles they're predicted to have? And the answer is you could do that, but you would need to calculate a new line. Okay, if you're going to flip this problem to say, hey, if you have 10 cousins, how many aunts and uncles? Then you would need to recalculate the line using cousins as your explanatory and aunts and uncles as your response. And the simple reason I give you really comes back to this formula. If you just suddenly flip these two, that's not going to be the same as putting in 10 for cousins and solving backwards. okay? So just be aware, that doesn't come up often, but if you're going to try and work backwards, you shouldn't be working backwards with a regression equation. You would actually need a new equation. Finally, find the residual. Residual is defined as, I'm going to put R, the actual data point, okay, minus the predicted point from the line. I always remember this because it's AP statistics, so it's A minus P. So I go up 11 aunts and uncles. Let's find that. So here it is, 11 aunts and uncles predicts 11 cousins. So we say, all right, 11 minus the predicted amount. So we'd say, well, negative 1.29 plus 1.34 multiplied by 11. And this comes out to be negative 2.45 if you type that in. This is our residual. This is how far away our line predicted compared to the actual number. So this, of course, is interpolation, or used for interpolation. And the fact that it's negative means, obviously, that our prediction was higher than the actual number. So we were overestimating using the line. The whole point of least squares regression line is to be able to predict, right? So we have to have confidence in our line that comes from being a good fit, from having a high correlation, and we need to be able to use it in a way that is appropriate.